Chapter 6, we're looking at thermochemistry. Thermo refers to heat, as in thermometer, thermodynamics, thermochemistry. This chapter is going to look at the heat flow as chemical reactions occur. There are two ways that heat can flow. We can have a system that is endothermic. Endo means into. So an endothermic reaction, heat flows into the system. The other kind of system we can have is an exothermic system. Exo meaning out of. An exothermic system, heat is being given off by the reaction. A couple of ways we can represent heat, and more specifically heat flow, which way the heat energy is moving. The symbol we're going to use to represent heat flow is Q, and Q is directional. It's how the heat is moving into a system or out of a system. If Q is positive, it is an endothermic reaction. If Q is negative, it is an exothermic reaction. So heat is moving out of the system for exothermic. Heat is moving into the system if it's endothermic. What we also need to look at is something called heat content or enthalpy, and that's the amount of heat contained in a substance because of the bonds holding the different atoms together. Both heat flow and heat content are measured or recorded in joules or kilojoules. The relationship between heat flow and other parts of the reaction, you've seen this reaction before when you're dealing with specific heat. It's the heat flow is equal to the mass of substance involved in the reaction times the specific heat of the substances in the reaction times the temperature change of the system. Now, at constant pressure, that means essentially when we're running reactions open to the atmosphere, so atmospheric pressures inside and outside the system, we can rewrite this equation so it looks like this, where the heat flow Q at constant pressure equals the enthalpy of the products, the heat content of the products, minus the enthalpy of the reactants, or the heat content of the reactants. And so the main idea here is Q is equivalent to delta H, or the change in enthalpy. We can't measure enthalpy. We can't measure how much heat is contained in something. What we have to do is determine enthalpy of something by measuring the change in heat. We measure the change in heat by looking at the change in temperature of a chemical reaction. For example, if we're looking at this reaction right here, very simple, we've got hydrogen plus half a mole of oxygen forms water. Turns out the heat flow equals the enthalpy of 1 mole of water minus the enthalpy of 1 mole of hydrogen plus the enthalpy of a half a mole of oxygen. And we find that is 285.8 kilojoules. It's negative, so that's an exothermic reaction, or when I combine hydrogen and oxygen, heat is given off to form the water. As with Q, when delta H is negative, it's an exothermic reaction, so my products have less energy than my reactants. Heat is given off from the system. When my delta H, or enthalpy change, is positive, I have an endothermic reaction. In this case, the products have more energy because energy has been absorbed during the course of the reaction, and therefore products have more energy. You've dealt with conservation of mass. We did it when we were dealing with stoichiometry. We're now looking at conservation of energy. And we know that, or we have been told that the total amount of energy in the universe is constant. And it's been constant as long as the universe has been around. We can't create energy. We can't destroy energy. We can simply convert it from one form to another. And when we're looking at the universe, we have two parts to our universe. The universe is equal to the system we are working with and the surroundings. The system is the chemical reaction we are looking at or studying. The surroundings is everything else. So when we're looking at thermodynamics, we really have two parts. We have system and surroundings, and that makes up the universe. So when we were looking at our example before where hydrogen plus oxygen form water, energy is transferred from the system to the surroundings. So it's an exothermic reaction. And so the energy stored in the bonds as potential energy decreases. That is energy that's given off. And the kinetic energy, the energy of the motion of the particles, Kinetic energy increases because as things warm up, the particles move more quickly. So we have kinetic energy increasing, we have potential energy decreasing, and so what we have is the reactants had more energy compared to the products. For endothermic reactions, it's going to be the reverse. So for endothermic reactions, the products end up with more energy, so my potential energy is going to increase, so I get more energy stored in the bonds. Since the temperature is dropping, the particles are moving more slowly, the kinetic energy is decreasing. And so in this case, the products have more energy than the reactants did because they've absorbed energy from the surroundings. There's several thermodynamics laws. We're going to work through those. The first law is that the enthalpy or the heat content is proportional to the amount of stuff you have, or H is proportional to mass. So if we take a look at this reaction where we have hydrogen peroxide as a liquid decomposing and it goes to water and oxygen, we have an enthalpy change of delta H of negative 98.2 kilojoules. So it's exothermic. And this is 1 mole of hydrogen peroxide, 1 mole of water, and half a mole of oxygen gives us that much energy. So instead of a mole, if we have a gram of hydrogen peroxide, what are we going to get for energy this time? So the math we're going to do is going to look like this. We're going to take the kilojoules per 1 mole of hydrogen peroxide, which we got from the reaction above, divide by the formula mass of hydrogen peroxide, and we're going to get the amount of kilojoules per gram that are present when we run the reaction with only 1 gram. Okay, enthalpy is also temperature dependent. That means as the temperature of the system goes up, the amount of energy contained in the substances, in the compounds and the elements, also increases because it's a measure of the amount of energy in the bonds. Usually when we're dealing with enthalpy, we're looking at it under standard conditions. For thermodynamics, standard conditions are temperature is equal to 25 degrees Celsius or 298 Kelvin. Not 0C, because they usually run in laboratory conditions, and 25C is pretty close to a little bit warmer than room temperature. So when we look in tables of delta H, we're going to find they're given for values at 25 degrees Celsius. Enthalpy also depends on the phase of the substance. So the enthalpy for liquid water is not equal to the enthalpy for gaseous water. And so we have to make sure that we know what phase we're working with when we write these chemical reactions. So the change in enthalpy for the forward reaction and the change of enthalpy for the reverse reaction are numerically the same. What is different is the sign. So if we look up at number 1, we had hydrogen peroxide decomposing. We had a negative delta H, negative 98.2 kilojoules. If we look at the reaction here with number 2, we've got water and oxygen combining to form hydrogen peroxide. Phases of each of the substances are the same if you check the 2 reactions. Here we have a positive delta H. So the values are the same. Direction is important. So you need to know which way you're going. Third thing we're going to look at is enthalpy is a state function. Well, what does that mean? Well, it means that enthalpy is like a vector. It's directional. And the change in enthalpy is simply the difference between the starting point and the ending point. So if I have 3 steps in my reaction, the enthalpy is the difference between beginning and end. So we only are interested in the energy of the starting reactants and the energies of the final products. The intermediate steps doesn't matter. However, if we have multiple steps and we can't find the change in energy from the beginning to the end, sometimes we have to take the steps into account. And when we do, then we're looking at a process called Hess's law. If we take each of the steps and we add them together, we get the change in heat of the reaction is equal to the sum of the heat change for each step. And sometimes that's the only way we can figure out what the total energy changes is by going stepwise. When we do this, we're working through something called Hess's law.